6.1, day number 1, velocity and net change. We're going to review position, velocity, acceleration, and connect them with net area under the curve. So position, velocity, acceleration are related in this way. ds dt, right? That's the change in position is velocity. d2s or d squared s dt squared is the same as acceleration, right? So that'd be the same as the derivative of the velocity, or you could call that dv dt. All right, how do you know if a particle is moving to the left or to the right? Well, it's moving to the left if the velocity is less than 0. It's going to be moving to the right if the velocity is greater than 0. How do you know if a particle is speeding up? Okay, so speeding up happens when both the velocity and the acceleration have the same sign. Okay, same sign, and slowing down if they have opposite signs. Slowing if velocity and acceleration have opposite signs. Alright, so if velocity is negative, the object is moving to the left. If velocity is positive, object is moving to the right. Sign of acceleration is the direction of the force on the object. An object is speeding up if, like we set up here, velocity and acceleration have the same sign. Slowing down if they have different signs. So what is the difference between distance and displacement? So distance and displacement. So distance is the total of how far object traveled. Okay, whereas displacement is the change in position. Okay, with reference to the starting spot or where you started. Alright, give an integral equation for displacement. Well, an integral equation for displacement would just be the integral from a to b of velocity dt. Total distance would be a little different. We want all distances to be positive, so we can just add them all up. So we take the absolute value of the velocity. Okay, so let's say this is our velocity function. Let's just, for the sake of this, make up some numbers. Let's say this area is 12. It's a 12. There we go. This area is a negative 15. And this area is a 20. Okay, so displacement would be red plus blue plus green. Okay, which would be 12 minus now, recall that it's negative 15 plus 20. Alright, which looks like it'd be, what, 17? So our displacement is 17 units. Our distance, though, would be 12 plus 15 plus 20, which would be 47. So if a total distance traveled is different than displacement in that way. Alright, so let's get our calculators active here and find the displacement. Okay, so we'll do from 0 to 5 of this function v of t dt, and do the same thing, except let's find total distance using absolute value of v of t dt. Get an answer, and let's check them. Alright, so I got a displacement of 35 units and a velocity of 42.586. So in summary, if we integrate velocity, we get displacement, the net area between the velocity curve and the time axis. If we integrate the absolute value of velocity, we get the total distance. Alright, so if a particle moves with a constant acceleration of negative 32, then its velocity would be the integral of that, which would be negative 32t plus c1, and its position would be negative 16t squared plus c1 times t plus some other constant, let's call it c2. Okay, this is, by the way, acceleration due to gravity on Earth. Okay, so this value right here, I'm going to assign a variable to, and I'm going to assign another variable to this. Alright, this is going to work in this case and not necessarily in others, but only with this gravity situation. Okay, so C1 is actually the velocity at 0, so the initial velocity. So we're going to call that V sub 0. So position function is actually equal to negative 16t squared plus the initial velocity times t plus the C2 value is actually x of 0, so its initial position, which is the initial height. All right, and that should look very familiar to you. Now in the next scenario here in example 3, it's a little bit different. It no longer follows this idea of gravity because it is exponential in nature, and we know that gravity is quadratic in nature. Okay, so let's take a look at it. So the acceleration in this situation is e to the negative t. That means that our velocity is going to be negative e to the negative t plus c. And let's see here. I'll just leave that as c. So our velocity function, we don't know the constant for, as you can tell here, but if I did a quick substitution, I could find it, right? Because I actually have enough information in this case to find that value. We're told that the initial velocity is 60 feet per second. So this value here is 60. Negative e to the 0 is 1. Excuse me, negative 1. So therefore c equals 61. So our velocity function with respect to time is negative e to the negative t plus 61. Okay, now let's find x of t, which would be the integral of this. So x of t would be the integral of what we have here as v of t. So it would be e to the negative t plus 61t plus c. We know our initial position is 40, so x of 0 is 40. So 40 equals e to the negative 0, right? E to the 0 power plus 61 times 0 plus c. Well, then that means that 40 equals 1 plus 0 plus c. So that means that c equals 39. So our velocity function with respect to time was negative e to the negative t plus 61, and our position function would be e to the negative t plus 61t plus 39. There's our position and velocity functions based on the information given. Alright, the function v of t is the velocity in meters per second of a particle moving along the x-axis. V of t is given between 0 and 3. We want to know when the particle is moving to the right, when the particle is moving to the left, and when the particle is stationary or stopped. So in order to determine where the particle when the particle is moving to the right, we want to know when v of t is greater than 0. To the left, when is v of t less than 0. And stationary, when is v of t equal to 0. Okay, so just by inspection alone, I can tell you right now that the velocity will never equal 0. Actually, I'm sorry, the velocity will equal 0, but it'll only be at 0. So the particle will be stationary when t equals 0. That's the only time. As you plug in values, right, between 0 and 3, inclusive on that, you'll never get a negative number. So this won't apply. The particle will always either be stationary or moving to the right. And so then I would say if t is greater than 0 and less than or equal to 3, then we'd have a particle moving to the right. So find the particle's displacement for the given time interval if the initial position is 3. What is the particle's final position? Okay, so let's think about displacement. Remember, displacement is the integral from start time to end time. All right, this will be our displacement of v of t dt. Okay, so this will tell us the amount of distance traveled in which direction, where it ends up. Does it end up to the right of its initial position or to the left? So take out your calculator, go ahead and do that real quick and get an answer. So I get a displacement of 1.151. Okay, that's the displacement, so it ends up 1.151 units to the right of its initial position. So what I would do here is I would take s sub 0 and add it. Okay, its final position would be s sub 0 plus the displacement. So if I add s sub 0 to this, I get 4.151. That would be its final position. Okay, for total distance traveled, I'd do the same thing, except now I'd use absolute value of the velocity. That will make all distances positive. And in this case, because it's only moving to the right, it never comes back to the left, the displacement and the total distance are going to be the exact same. Okay, here you've got some summary notes on position, velocity, displacement, distance traveled, and all that good stuff. I would look these notes over and go ahead and just kind of give them some time to set in. Okay, so look at them pretty much every night, I would say, just to be familiar with them and be able to use this idea of finding a position or a velocity, for that matter, finding velocity from acceleration based on this idea of displacement versus distance. Alright, I'd like to do maybe these last couple of examples and then call it a day. The acceleration of a particle moving along a coordinate line is this. If the velocity at time t equals 0 is 4 meters per second, find the velocity 2 seconds later. Try this problem algebraically. So I'm going to use a calculator first. So I'm going to do the integral of v of t dt from, what is it now? 0 to 2. And because I want the velocity, find the velocity 2 seconds later, this will try and find me the displacement of velocity, or the change in the velocity, but I'm going to add that to the initial velocity. So I'm going to add that to v of 0. Okay, and that'll find me the velocity at time 2. Okay, so for my integral, my change in velocity, the displacement of velocity, I get 0.023. Therefore, my velocity after 2 seconds would be the initial velocity, which is 4 plus 0.023. So that tells me that the velocity at time 2 is 4.023 meters per second. You can go ahead and try that problem algebraically. I'm not going to do that on this video. Alright, so let's look at example 6. For the following problem, the graph of the velocity of a particle moving on the x-axis is given. The particle starts at x equals 2. Okay, so what that tells me is that the position at time 0 equals 2. I'm going to use that. Find where the particle is at the end of the trip. Okay, so if I want velocity, I want position after 5 seconds. That's going to be position at time t equals 0 plus the integral from 0 to 5 of v of t dt. Now I don't have a function assigned to this, so I can just use the area under the curve from 0 to 5. Now notice that these two values here and here, those will negate each other. Right, so those are just kind of canceling each other out. So it's traveling right and then traveling left the same amount. So I'm just going to find the area of these two, this triangle and that rectangle, and that will evaluate and give me the total distance traveled. So x sub 5 will equal the initial position, which is 2, plus whatever the blue areas are that I've calculated there. So it looks like the first area will be a triangle. That'll be 1/2 base times height. Looks to me like that'll end up being 1. And the second one will be base times height, which is 2 times 2, which is 4. So the total distance traveled there would be 5, and the position at time 5 would be 7. Alright, for part B, find the total distance traveled. That just means I want every distance to be positive. So I've got my distance of 1, distance of 4. I believe these are both going to have the same absolute value as the first one, which would be 1 and 1. So therefore it looks like the total distance traveled would be 7. Now don't get that confused. In part A, this is the final position, right? This is the distance traveled. Now how could that be? That's because we started at x equals 2, okay? So we backtracked 2 units. From 2 to 9, we backtracked back to 7. And so our total distance traveled in this case coincidentally is the same as the position at the end of the trip. Alright, that's it. That is 6.1 day 1 velocity and net change.